Okay, so last time we talked about how to calculate the mean and the range and the standard deviation for a distribution. And today we're going to talk about interpreting that standard deviation, or really a practical interpretation of the standard deviation. And it's more difficult to interpret or to get a feel for what's going on than the mean or the range is. But one way that we can do that is to consider the number of observations that fall within some specified interval, okay, where that interval is a function of the standard deviation. And the two procedures that we're going to talk about for doing this are Chebyshev's theorem and the empirical rule. So first, in the case of Chebyshev's theorem, it says that given a data set of n observations where they are x1, x sub 2 to x sub n, and z is greater than 1, and here the important thing is that z is going to be equal to the number of standard deviations. Okay? And oftentimes with Chebyshev's, z will be equal to 2. That'll be important, as you'll see as we move through this. But what the theorem says is that given all of that, we can be sure that at least 1 minus 1 over z squared percent of the observations will lie within that number of standard deviations from the mean. And so therefore, if we can work this out, if, for example, z is equal to 2, and we work that out, we could say that 1 minus 1 over 2 squared, which would be equal to 3/4, or 75%. So if z equals 2, we know that at least 75% of the observations, however many there are, if there's 100, that would mean 75 of the observations, will lie within the interval that we can denote of the mean minus 2 times the standard deviation, and the upper bound is the mean plus 2 times the standard deviation. So within that interval, if z equals 2, at least 75% of the observations will fall. And we also can know if z is equal to 3, we could work that out, but I'll just write it here, at least 89% of the observations will lie within 3 standard deviations from the mean. So let's take a look at a little example here. But before we do that, if I were to draw this out, say I have a bell-shaped distribution, for example, and the interesting thing is we'll get to, Chebyshev's we do not have to work only with bell-shaped distributions, but if we did, it would look something like this, where we had mu plus 2 and we had mu minus 2 times the standard deviation. And within this interval, we could be sure that there would be at least 75% of the observations. Okay, so let's consider, for example, that we have 60 observations with the following point estimates, where mu is equal to this and standard deviation is equal to that. So if z were equal to 2, then we would know that at least 75% of the observations will lie within the interval 6.0033 minus 2 times 2.31, and the upper bound of 6.0033 plus 2 times 2.31. Okay? Or in this case, that interval is 1.378 and 10.62. Okay? So the advantage of Chebyshev's theorem is that we can use it, make a little error there, with any distribution. Okay? So we don't need to know the shape. We don't have to have any idea about the distribution. But the drawback or the disadvantage is that it is too conservative. Okay, and so what do we mean by that? Well, it tends to underestimate the number of observations that actually do lie within that interval. In other words, usually it's often more. And so we can use the following procedure. We can find it much more useful when we know the shape of the distribution. So let's take a look at that. And this procedure is called the empirical rule. Okay, so if we know, or we can assume, that the distribution is normal, mound-shaped, bell-shaped. Okay, we just drew a little picture out like that. So it's symmetrical, basically. If we know that it's fairly symmetrical, then we can use the empirical rule, and we will know then that within one standard deviation, okay, so this first one here is one standard deviation, we know that that interval should contain approximately 68% of the observations. Within two standard deviations, the empirical rule says that that interval should contain approximately 95% of the observations. And within three standard deviations, the empirical rule says that that interval should contain approximately 99.7, or for all intents and purposes, virtually all of the observations should be contained within that interval. So if we had that sample of 60 observations, where we had those point estimators for the mean and the standard deviation, we would expect to see something like this. 68% of the observations should be within the interval of 6.0033 minus 2.31, and that interval of 6.0033 plus 2.31. Okay, so within that interval, 68, and you could go ahead and do that for 2 standard deviations and 3 standard deviations. And we could calculate the number of observations that we would expect to see within those intervals. Okay, so a couple of final notes. The first one is that both of these, the Chebyshev's theorem and the empirical rule, which are guides to help us estimate the number of observations that fall within an interval, really help us to describe the distribution of a data set. And under both rules, especially the empirical rule, it is very unlikely to see observations much more than 3 standard deviations away from the mean. Observations that are more than 3 standard deviations from the mean we call outliers. And we'll talk about that next time. So I hope that you found this helpful, talking about the empirical rule on Chebyshev's, and we'll see you next time.